let's talk about the notes on 11.1 and 11.2, but the back side. So first, area formula for a trapezoid is 1/2 height times base 1 plus base 2. So the reason we have two bases of a trapezoid is because we have two sides that are parallel to each other, but those two side lengths that are parallel to each other are not the same length. So that's why we have two different bases, a base 1 and a base 2. And then the height, of course, needs to be perpendicular to those two bases. The height will not always go up and down. Sometimes your bases go up and down, and so your height goes horizontal. Just make sure that your height is perpendicular to your bases. So, first example, clearly a trapezoid. It tells us that our bases are 3.6 and 6 meters. And we can tell that 5.8 is the height because it is perpendicular to the bases. So when we plug in everything into our formula, we have 1/2 height times base 1 plus base 2. And so just be careful when you're typing that into your calculator. Make sure you put parentheses in the appropriate places. Or if you're doing this by hand, mental math, make sure that you are doing order of operations correctly. Add your bases together first, then multiply by the 5.8 and the 1/2. And you should get an answer of 27.84 meters squared. All right, second one, also a trapezoid. Again, our bases are these two horizontal pieces. And then this we can tell is our height because it's perpendicular to our bases. So we have 1/2 height times base 1 plus base 2. So when we add all of that together, we have 1/2 times 4 times 14, or 28 feet squared. Feet were our units on that one. Same slide, two more examples. Make sure that you take the time to identify what type of shape we have first. So this first example is clearly a kite. We have two pairs of consecutive congruent sides. So we're going to use our kite formula, which is 1/2 times diagonal 1 times diagonal 2. And it gives us both of our diagonals for this example. It tells us that the diagonal this way is 6. The diagonal that way is 14. Do those have units? Inches are our units that we're working with here. And so we have 1/2 6 times 14, which is 42 inches squared. Don't forget to square your units because we're dealing with area in this chapter. The next shape is a rhombus. We know it's a rhombus because all of the sides are congruent. Now, a rhombus is a parallelogram. So if you know the base and the height, you can use the same formula that we would use for a parallelogram. But in this case, we don't know the base or the height, anything perpendicular to it. So we have to use the other formula, which is the same as a kite, 1/2 of diagonal 1 times diagonal 2. But we don't know the full diagonals either. It gives us part of the diagonal. So you have to remember your properties when we talked about parallelogram properties. And for a rhombus, for all parallelograms, the diagonals are bisected. So if this much of the diagonal is 30, that means the whole thing is 60. And if this part of the diagonal is 40, that means the whole distance across is 80. So our two diagonals are 60 and 80. So our formula will say 1/2 of 60 times 80, and we get 2,400. And our units on this one are meters squared because it's area. We are on slide 2 on the back now. We have a word problem where it says the diagonal of a kite is twice as long as the other diagonal. The area of the kite is 72.25 square inches. What are the lengths of the diagonals? So anytime we have to find a missing dimension, start by writing down the area formula or whatever formula that we need. In this case, we're talking about kite. We know the kite's area, and the area formula for a kite is 1/2 diagonal 1 times diagonal 2. And we know that area, so I'll go ahead and substitute a 72.25 there for the area. We don't know either diagonal though, and we need to find them both. But it does say one diagonal is twice as long as the other. So we'll call it diagonal 1 is in math means equals, twice as long as the other, 2 times the other. So 2 times diagonal 2. Sorry, it's hard for me to write on here. I'm running out of room. So diagonal 1, we'll just, instead of writing diagonal 1, we're going to write 2 times diagonal 2. We're substituting there. Times diagonal 2. So the reason we do that is now we only have one variable in our equation, diagonal 2, instead of 2 separate diagonals in our equation. And when I saw this, this is really similar to one we did on the front side. The 1/2 times 2 is just 1. We have 2 d2s, diagonal 2, so we're squaring that. So if we take the square root of 72.25, I have that written down, it is 8.5 inches. So diagonal 2 is 8.5 inches. And since that is one diagonal, if I plug that in up here, I know if I multiply that by 2, I'll get my other diagonal. So if I take 8.5 times 2, I get 17 inches. So my other diagonal must be 17 inches because it was twice as long as the other one. For the next example, we're going to find the area of a rhombus, and I did not give you a coordinate plane to graph these points on, but we can find it without a coordinate plane. So it gives us the points. We know our area formula for a rhombus is 1/2 diagonal 1 times diagonal 2. So we need the lengths of our diagonals. So using those coordinates, our diagonals are MP and NQ. So the vertices that are not next to each other create the diagonals. And if I want to find the distance between N and Q, we need to use the distance formula. So pause the video and find the distance of NQ and MP using the distance formula. Do you have it? NQ should be 4 and MP should be 8 when using the distance formula. So then when we plug those into our area formula, we have 1/2 times 4 times 8, or 16 square units. The next slide, we know this first example is a trapezoid because BC and AD are parallel to each other. They both have a slope of 0. We know that because we have a coordinate plane. And we know that that grid, the coordinates are going up by tens. So we're going to use that information to go ahead and find all the information that we need. So our area formula for a trapezoid is 1/2 height times base 1 plus base 2. So base 1 and base 2, we've got BC and AD. So using that, each coordinate is actually 10 units. Go ahead and count across. So AD looks like is 7 across. So if each one is 10, that means from A to D is 70. From B to C looks like 4. So since each one is 10, that's 40. And then we can also calculate the height by going from B to E because it's perpendicular to our base. So from B to E, that looks like 5 or 50. And then once we have all of our information, we're just plugging that into the formula. The height is 50. Our bases are 40 and 70. So we have 1/2 of 50 times 110, and we get 2,750. The units for that problem were meters squared because it's area. Another example where we're finding a missing dimension. It tells us the area of a trapezoid, but we're missing what the bases are. It must have tell us the height too. Yeah, the height is 3. I missed that information. So when we are looking for missing information, start by writing down what formula you're going to use. In this case, we're using the area formula of a trapezoid, and then plug in what we know. We know the area is 13.5. The height is 3. We don't know base 1 or base 2. So let's just call base 1 x. And then once again, it says one base is twice as long as the other base. So if one of the bases is x, the other base is 2x. Or just like we did on the previous examples, you could use base 1 and 2 times base 1, or base 2 and 2 times base 2. Doesn't really matter. In this case, I'm just using x's so I don't have to deal with the subscripts. So if I'm calling base 1 x and base 2 2x, this is what my formula looks like when everything is plugged in. So x plus 2x, that makes 3x. So I have 13.5 equals 1/2 of the height 3 of the added bases 3x. So I have 1/2 of 9x or 4.5x. And let's see, I did that example wrong on my notes actually, so I need to grab my calculator. 13.5. Under my paper. Okay, so we have 1/2 of 9x is 4.5. 13.5 divided by 4.5 is, 3. I guess I didn't need my calculator for that. So x is 3. So that means one of your bases is 3, which makes the other base 6. And our units here are feet. We just have time to go over one more example, so I'm going to do this one. You can find it on the last slide. This is not a shape that we're familiar with, so what we're going to have to do is cut it into shapes that we are familiar with. So I can kind of see a natural dividing line right here that creates a rectangle on bottom and a trapezoid on top. And we know the area formula for a rectangle, and we know the area formula for a trapezoid, so that works out in our favor. So we have this rectangle on bottom. There's lots of coordinates going on here, but if we're just looking at the rectangle, our base is 10, our height is 6, so the area of that rectangle is 60. The trapezoid is a little bit harder to figure out. I'm going to write the formula up here. In this case, our bases are these two sides because they're parallel to each other, which means this distance is the height. So out of all those things that we need, we really only know one of our bases is 8. We need to figure out the other base, and we need to figure out that height. So here's our height. Because I know this whole distance is 10, and this part is 4, that must make this part 6. So the height of that trapezoid is 6. We're going to use that same logic to figure out this little piece right here. I know this whole side length is 9, and this much of it was 6, because that's part of our rectangle. So that missing piece must be 3. So when I find the area of that trapezoid, I have 1/2 of 6 times 11, or 33. So the area of the trapezoid is 33, the area of the rectangle is 60, so that means the total area, once we add those two together, is 93, and our units are feet squared.